All right, thank you very much, Mark. On the contrary, thanks a lot for the invitation, and obviously to all the organizers, and also a big thank you that comes also with an apology. The thank you to Diego Buccio for taking my spot a couple of weeks ago. I had some conflict, and he super kindly accepted to take my spot. So thanks to that, I can talk to you here today. So also thank you, and sorry for the inconvenience. And that being said, as Mark kindly introduced, I will be talking to you today about this one recent work that we titled Cosmology from Asymptotically Safe Proca Theories, even though at the moment is more the asymptotic safety part and the cosmology part will come very soon, hopefully. And I was wondering how I should start, and I thought it would be a good idea to benefit from an asymptotic safety seminar from a couple of weeks ago that Sara Aliberti presented. And the reason for that is that this is actually one out of two almost parallel works on generalized Proca theories. And the last time we coincided, I could only express my enthusiasm by the fact that these theories are being so studied at the moment. And at the personal level, I will benefit from the talk she super amazingly gave, introducing all of them, and hopefully she also took all the difficult questions, so I can go directly to my work. But yeah, that being said, I just wanted to stress this in case you want to visit the other paper as well. I like to see these two papers as complementary, just because they, in general, establish different truncations, work on different truncation setups, and in general, of course, the fixed point structure is slightly different, even if for many things we do also agree. And yeah, whenever possible, I will try to put them in perspective. But in general, I will obviously be talking about the one on the right, which is a work that I did mainly with Alvaro, Jan, Manuel, Lavinia on the cosmology side. And that's it. So you're very welcome to ask questions, and let me know whenever there is something you would like me to elaborate a bit further. All right. So the audience is as specialized as it gets, so no general effort introduction is needed. But I would like to start maybe with the broader picture and a brief motivation of the kind of study we wanted to pursue, also beyond generalized Proca theories, and just like what our broader perspective would be. When I'm done with that, I will introduce very briefly, because as I said, Sarah already did a great job with that in detail a couple of weeks ago, but I will go maybe to the point that I need for stressing the importance of GPTs in cosmology. And then I will go hands down to business and introduce to you what truncation we use, why we did the work the way we did it, how this was implemented in the vertex expansion in the fluctuation fields, which is ultimately the setup we use for our study. And then I will spend most of the time probably for sharing with you the fixed point analysis, what we found, the limitations of the approach, the improvements we want to do, and how the situation looks like. All right. So if I can answer the questions you have um, on the screen right now by the end of the talk, then I will be very happy. And if not, please ask me again, and I will stop. All right. So regarding the overall motivation, this is a picture that the CERN created. These cute cartoonish pictures when they refer to the zoo of particles we observe nowadays. And when I was looking at it, and we were discussing also with other people, the thought is like, well, we do indeed have a zoo of particles, but if we think about it, we can also say that we have like a zoo of effective theories and modified gravity theories in general. And all of these theories, when they enter a cosmological setup, some of them are ruled out within some parts of the parameter space. Other ones have like very strong constraints, bounds, etc. But in general, most of them are valid as effective theories in the regime we measure them. But they have not been receiving that much attention, maybe from the asymptotic safety perspective. Of course, there are many works on cosmology by many people, some of them even present in the room. But it would be nice to maybe extend the existing studies, maybe on more like higher derivative gravity or Lenski gravity and this kind of setups to other effective theories for cosmology, and see for those that have been less studied, how we can constrain them and maybe get some cosmological predictions and in general see how we can use the quantum gravity filter or the asymptotic safety filter to study them in the infrared and get some nice predictions. So yeah, so I would say that the overall idea we had in mind when we started this work was not only studying like generalized Proca theories, but trying to do it maybe in a bit more general setup that I will share in a second, and hopefully also develop the machinery so that we can apply that to whatever, of course, within the technical limitations of computing flows, diagrams, etc. But within those limitations, trying to study any cosmologically motivated effective field theory for gravity and matter that we might be interested about, and see, of course, which regions of the parameter space of these theories belong to the asymptotic safety landscape. And ideally, if we can get predictions out of that, then it would be fantastic. So within this broader picture, we happened to start with generalized Proca theories, and maybe for people less familiar with them, they are simply vector tensor modified gravity theories with a broken U1 gauge symmetry. So we have a massive vector field, a spin one vector field that is coupled to gravity, and for those of you more familiar with Hornensky gravity, one can think about it. One can think of it as a spin one analog of Hornensky gravity. So if one, for example, starts with the ordinary Proca theory, the one that has just like the F mu nu and a massive term, this massive term breaks gauge symmetry. We have a longitudinal polarization that is no longer gauge redundancy, but it becomes a physical propagating mode. One can see it like using usually the Stuckel vector composition and make it like this longitudinal sector appear or pop up as some scalar field. And the motivation behind generalized Proca theories is very natural, and it's just answering, can we add derivative self-interactions for these massive vector fields in analogy with these condensate theories or Galilean theories, while propagating only these three healthy degrees of freedom? So the two transversal ones that we have, we already had before, plus the longitudinal one. And the answer is yes. So these theories keep second order equations of motion with no additional goals like propagating modes because of how the derivatives are arranged, and they propagate in this sense three healthy degrees of freedom at the cost of arranging these extra terms in a very specific and particular way. So if you happen to be interested in the details of these constructions, feel free to either go to the original paper that I'm citing here. I'm not sure if you see the mouse. I don't think you do. I moved. Yeah, well, you don't see the mouse for whatever reason, but never mind. Just I go to the first reference, or if you want someone explaining them to you, please go to the recording of Sarah's talk a couple of weeks ago. But yeah, in practical terms, we are dealing with this kind of gigantic action where the numbering is essentially labeling the position each term occupies within this Galilean-like hierarchy. Is like a cosmology inherited notation. It has nothing to do with, or not directly to do with the relevance of the operators or just like the number of fields appearing. It's more like we have like for the L3, we have the first derivative self-interaction. For the L4, we have the next level in the hierarchy that combines quadratic derivative structures with non-minimal curvature couplings, etc., etc. But this is the kind of theories we deal with. This is the most general action for GPTs. And the reason for studying them as an effective theory for cosmology is that they have quite interesting features. So if we, for example, wanted to evaluate them on an FLRW background, this vector field can take a purely temporal profile. And this is particularly relevant whenever we construct a solution that we do not want to break homogeneity and isotropy. And such a background can actually lead to non-trivial branches like accelerating solutions and an effective dark energy contribution. So we say that it leads to highly non-trivial cosmological dynamics in several ways, let's say. So it's like this phi of t is not, how to say, it's not itself an additional propagating degree of freedom at the background level, but it behaves as an auxiliary field whose value is algebraically tied to the Hubble expansion rate. through this background field equation, if that makes sense. So we have like a new component that can essentially contribute to an effective dark energy component, let's say, capable of sourcing accelerated expansion, and one of the most one of the most remarkable results in the literature is like some existing de Sitter solutions, etc., etc. So that is on the one hand side. And then on the other hand side, these theories have been studied quite a lot at the level of perturbations. And without entering into too much detail, for which maybe you can visit some references that I put here, they modify all sectors of cosmological perturbations. So they modified kinetic coefficients and propagation speeds, which is particularly concerning for gravitational wave propagation. They modify the effective Newton coupling, growth of matter density perturbations can lead to extra vector signatures beyond what one typically finds in scalar tensor theories. And probably the most interesting part of this is that these effects can show up in observables. So it's not just like a theoretical prediction, but these effects translate into non-trivial changes in some cosmological parameters that we can effectively measure. So just maybe as a very brief introduction for um, the audience that's familiar with these quantities, these GF measures essentially how strongly matter perturbations feel gravity on cosmological scales. So whether structures grow faster or slower than in standard GR. These eta slip would quantify the difference between two scalar metric potentials, governing the motion of non-relativistic and relativistic matter, and the F sigma 8 describes the observed growth of matter clustering, let's say. So the key point I wanted to make, and if you allow me to present to you a more cartoonish picture that I found cute to generate, is that the moment we can spot the fixed point structure and we can construct our critical hypersurface that we're all familiar with, these fixed point constraints will naturally translate into the infrared values of the Proca couplings, this GIX appearing in the Proca action, that will at the same time impact some tensor, scalar, and vector perturbation sectors, and we can actually like contrast that with observational tests, aka CMB tests, weak lensing, BAO, redshift space distortions, and gravitational waves. So this is the part we haven't done quite yet, but I would say is the ideal closure of such a study. We hope that even hopefully in both approximations and in both schemes, we can maybe make some sense out of them. But for now, we are still with the fixed point structure. And if this motivation is clear and we come back to the action, the absolute simplest subcase or subset of these GPTs that is compatible with all the aspects I mentioned before and that can lead to all these effects I mentioned before would be this one over here. There are, of course, many others, and we know how the game works. Ideally, we consider all possible operators and all possible ingredients that we expect the flow to generate, but this is classical still. I haven't done anything quantum. But at the classical level, this is the absolute minimum case we can do. So we include a genuine derivative self-interaction for the Proca field. We keep the coupling to the Ricci scalar as the standard Einstein-Hilbert one, and then well, we add also the mu term. So at the classical level, I insist, at the classical level, I will go to the quantum in two slides. This is the simplest we can go. Now, how do we play the game, or how did we play the game? Because there are different ways of doing it. Of course, we need to solve our old friend the flow equation. And for that, we need to adhere, or we need to follow some approximation scheme or some specific computational setup. And in our case, that was the vertex expansion in the fluctuation fields. So this means that instead of maybe considering an derivative expansion or including any other sort of ansatz for the effective action, we just expand it in fluctuation vertices. So these phi of xn would be the fluctuation field. And then we have to decide to which order we keep the tower and up to which endpoint function we include in the truncation. No, so the moment we establish that ansatz, computing functional derivatives of that will obviously give us the tensor structures of the endpoint functions, and then we will promote the couplings to individual entities, let's say, as I will explain in a second. And of course, they are followed by some wave function normalizations whose scale derivative will give rise to the anomalous dimension. So in short, we will get, as expected, and as it is common, the diagrammatic expansion for the different endpoint functions individually, and we will compute the flows of these correlation functions directly. Okay. And this is the main difference, let's say, in scheme with respect to the partner paper. So if this is clear, the recipe we have to follow is, when choosing a truncation, is twofold. In the first place, we have to decide which operators we keep in the effective action. Of course, the sweeter, the sweeter, the better. The more operators, the better. But we need to follow some criterion for that to make it in a way that we can handle. And that will be what we will generate the tensor structure of the vertices. And then in second place, we need to choose into which order we truncate the tower, as I already said. And that means making an ansatz for the behavior of the higher order vertices. So putting all together, the second cartoonish picture I prepared is essentially what we have to do. So these choosing operator content, constructing the vertices. The moment we have that, we can establish a dictionary between the fluctuation, between the fluctuation couplings and the couplings appearing in the Proca action that will allow us to make this correspondence between the objects whose flow we are computing and the ones that we will be measuring in the infrared. And of course, the last part is the flow and seeing which fixed point structure we have. So now I go quantum, and now, like continuing from what I mentioned before, I tell you which truncation we used. As I said, this is a minimal truncation. We're on that. So there are some things that we definitely have to include for the future, but this is so far what we made. And the results are, if I may say it, I think quite interesting, but I will go that in a second. But so this is just the adaptation of the simplest cosmological motivated subcase of GPTs that I presented before. We are just adding of course, the dressings and then writing it in Euclidean signature, etc. And then we are basically within this truncation, including all relevant and marginal operators by expanding the different Proca GI functions, which are in principle arbitrary functions of this invariant X. And for example, for G2, this acts as an effective potential, so there is no linear term. For G3, the term G30 is essentially a total derivative of the action, so it also does not play a role. And since we are again working on the fluctuation approach, we expand not only the metric but also the Proca field. And for this first study, we consider the background to 0. This, of course, this in principle will not affect in a first study, let's say, the flow, since we are directly working with fluctuation correlation functions. But this is another difference with respect to the other study. Okay. And for the G4 of X in the simplest cosmological setup I mentioned, this is taken to be the standard Einstein-Hilbert, but of course the flow does not understand of what is Einstein-Hilbert or not in the sense of operator content, and the term A squared R, for example, will be a marginal operator that we did not include and that we want to include in the future. Okay, so in short, when we add gravity gauge terms and gravity gauge fixing terms and the ghost action, we are left with this set of fields in this approach. So we will be computing flows for this graviton, Proca fluctuation, and the two Padiev-Popov ghosts. Okay. Good. So now that we are done with the first term, with the first step, which is essentially choosing which operator content we want to keep. The second one is the vertex construction. And in general, all our vertices will be written in the form some wave function factors, wave function renormalization factors, plus some running couplings, plus some tensor structures. The tensor structures, as I already said, are just the ones directly generated by functional derivatives of the operator content in the effective action, and the couplings will be promoted to be independent quantities that are in principle not tied to any others. Okay, this is one of the key points of this fluctuation approach. So how do we do this? So for the pure gravity sector, we essentially have this parameterization of the vertices, the T and H denoting precisely the tensor structure I mentioned above. And in this case, it has a momentum independent part, which is parameterized by this lambda Hn. And then we have the momentum dependent part that is parameterized by this GHn. No? So this we can call the level n coupling. And as I was stressing, it accounts for the fact that each graviton vertex in this fluctuation approach carries in principle its own independent coupling, which is one of the basic points of the formalism. And it is precisely here, this point, that it becomes important. So in this case, there is in principle no reason to assume from the outset that the coefficients extracted from different vertices must remain equal at the quantum level, let's say. And the different vertex couplings are commonly referred to as the avatars of the same classical coupling. Okay, so this is what we will call the avatars of the Newton coupling and the avatars of the cosmological constant. And to some extent, we are not doing anything new here. I'm just reviewing it for those of you who might be a bit less familiar with the formalism, but essentially it's the exact same approach that is done in basically all pure gravity fluctuation works, and also to some, like the last two are gravity matter systems. So there's nothing new in here. And for the Proca sector, this is a new part. We will also be considering a two-point function that also has two parts, like a momentum-dependent part and a momentum-independent part that will give us information about the Proca mass term. And then for the higher order vertices, let's say fluctuation vertices, each one will come with its own coupling. So we will have like Proca cubic interactions, quartic interactions, and so on and so forth. So how did we decide to truncate the tower? Well, we chose to compute this set of vertices here. So we will be computing we have computed the flows of the graviton 2-point function and 3-point function, and Proca 2, 3, and 4-point function. So in the fluctuation approach for the pure gravity side, this will give us the flow of these three parameters that you see here, which are the mu h, which is the graviton mass parameter, and is related to the level 2 cosmological constant, even if it's not appropriate within this formalism to call it cosmological constant. And then what we will be referring to as the avatar of the Newton coupling and the avatar of the cosmological constant. And in the Proca sector, the 2-point function will give us information about the Proca mass, and then we will have the cubic and the quartic couplings for the Proca. And this comes at the price of making these ansatz for the behavior of the higher order vertices. So in the gravity sector, we'll be identifying the behavior of all higher order vertices with the one of the 3-point function, which is again nothing new. This is inspired by, you can, for example, check these two works in here. It's usually inspired by classical diffeomorphism invariance, justified by effective universality, which is the topic of these two papers. You're free to go there if you want more details. But basically, doing so just means that although I have been saying that different vertices need not remain exactly equal once quantum fluctuations are taken into account, experience and previous work shows that these different gravitational avatars tend to stay sufficiently close for this identification to provide a reliable, let's say, efficient truncation. So this is what we're doing on the gravity side. And on the Proca side, we are going to resolve for on top of the mass, the 3 and the 4-point functions, so all the ones we basically neglect in this slide. So we need to compute the flows for these couplings here. This is what we did. Essentially, this system of 6 couplings. Okay. And The last piece I wanted to talk to you about, this final ingredient of this truncation, concerns the longitudinal part of the vector two-point function. And how to say, as I discussed before, these Proca theories propagate three healthy polarizations. So we have the two transverse ones and are already present for a massless vector field, and then this one additional longitudinal mode. And the most general Proca propagator also contains both transverse and longitudinal contributions. And there are different ways of tackling this. What we did is these are not gauge theories. Proca theories are, of course, not gauge, but not only not gauge, but they are in general not protected. The structure of GPTs is not protected by any symmetry. But what we wanted to do is, in order to maybe scan a broader set of theories, not only what one would refer to as Proca theories with all the longitudinal mode there, but also other gauge-like theories that I will share with you when I share the fixed point structure. We introduced this sort of pseudo gauge fixing parameter, which basically parameterizes how the longitudinal sector is treated. So it will not change the interpretation of the theory as a massive vector model. It will just give us a convenient handle, let's say, on the longitudinal fluctuations entering the flow. And in general, that means that we are considering this two-point function here. So with this new parameter, the moment we send psi to infinity, that limit will mean an answer plus longitudinal mode, and because of that, we will have a genuine Proca regime. But we can also interpolate all the region in between and make it to the psi going to zero limit, which is a very strongly suppressed longitudinal mode. And even if the theory is not gauge, intrinsically gauge, we expect it to have a gauge-like behavior. So the combine, well, we maybe share this last point, which is that conclusion over there. This is sorry, I forgot to mention, but I'm seeing there the reference. This approach has also been used for massive vector mesons and mesons in this paper you have in here, in case you want to give it a look as well. But yeah, what I wanted to say is that the fact that in the fluctuation approach, the couplings are independent, not tied to the specific action we are considering, other than how the tensor structures are generated because of taking functional derivatives, together with how we are considering the inclusion of the longitudinal term, the longitudinal mode, sorry, basically allows us to, using a common language, study not only the UV fixed points of Proca type theories, but also the ones that resemble those of abelian and non-abelian gauge theories. So that is the reason why we did that. So again, it's just not a gauge fixing term. It is a parameter we can use to control the longitudinal. And well, at this point, we are almost done. We know how the story goes. We need to solve the left-hand side and the right-hand side, which means essentially projecting the flows to isolate the beta functions and then computing the diagrams. And just in case there is someone who is, I don't know, maybe master student or someone who has not done this kind of computations themselves, I wanted to give just one slide to show how this is done. So consider, for example, the two-point function, which just projects in such a way that we can isolate the contribution from the coupling we're interested in. In this case, it would be the Proca mass that we are expressing here in a dimensionless form. Then we just take the scale derivative, and this gives us the form of the beta function. This is the left-hand side. And then this part over here is the right-hand side, which is essentially solving the diagrams directly. So for this specific endpoint function, the diagrams we will be solving are these ones here, where the wiggly lines are again the Proca fluctuation, and the double lines are as usual the graviton. And I didn't write it anywhere, but for the sake of completeness, we are using the Lytton regulator. Okay. So this is it. And in general, these are the diagrams we were solving for within our truncation and with our, basically the vertices we chose to retain. And at the technical level, we use vertex span for the computation of the vertices. The question mark stands for some bug we found. So be careful when you use it for non-gauge theories. And then for the rest, it was form tracer to fun, and for the tracing part, some form codes Manuel wrote for speeding up the process that otherwise takes way too long in Mathematica directly. And when we are done, when we are done with these computations, then we can compute the fixed point structure, and this is where I guess I will be spending most of the time in what comes. So we do find a genuine Proca fixed point, and also quite some more. So let me make this a little bit bigger and go one by one. So the first fixed point we found is what we call minimal, which is this one here. And it is basically a fixed point that exhibits vanishing matter couplings. So it is, I wrote here that it is essentially the U1 abelian analog of the minimally coupled non-abelian gauge theory fixed point studied in these references. And over here, as I said, it is not a gauge theory, but this specific fixed point has no Proca couplings. Well, sorry, that's not the correct way of putting it. The genuine Proca couplings, the values of the genuine Proca couplings at the fixed point are 0. So we expect it to have this sort of behavior. It has 5 relevant directions, which I will show you the critical exponents in a bit. 2 are associated with the gravity sector, and it's just the usual complex conjugate pair. And the remaining 3 are precisely the vector sector and are aligned essentially with the 3 parameters we are considering. Let's say the Proca mass, the cubic, and the quartic interactions. So in principle, I think this is it with this fixed point. So we can move on. Then the next one we have is the one that we call interacting fixed point. And in this specific case, we have non-vanishing Proca self-couplings, in particular the mass and the quartic one. The cubic one is still 0. And this fixed point has basically non-vanishing matters of, 4 relevant directions, which are the 2 gravitationals and then 2 vector directions, which are predominantly aligned again with the mass and with the cubic coupling, actually. And in general, well, we see how this fixed point exists for all values of psi, so it interpolates smoothly between let's say the Proca limit and the gauge limit we were mentioning before. And the Proca star fixed point, which is basically the genuine interacting Proca type fixed point. So this is the fixed point that does only exist for large psi. So for the cases where the longitudinal modes are not highly suppressed. In that sense, is why I wrote that there is no trajectory to an abelian-like gauge theory in the infrared. And it's more predicted than the other ones in the sense that it has 4 relevant directions instead of 5, 2 are gravitational and 2 are Proca. And for this specific fixed point, again, the cubic interaction is vanishing. And I think that's it. Yeah, because about the critical exponents, I will tell you in a second. That's it. And then the last 2 fixed points we find are the ones that we call Gemini, because with GPTs, we have to put Gemini somewhere as well to help advertise the work. And these fixed points, the moment you see the critical exponents, do not look particularly promising, but still they are there. They are called Gemini because they come in pairs. They are related by a conjugation of the cubic coupling. So you see it here in the plot, like the central right plot. Like there's a bifurcation, and in general, both share these two features. Sorry, the fact that they are conjugating G3 and they have finite coupling, cubic coupling, and other than that, they have different relevant direction coupling, and they exist only for finite size, same as Proca. But when we look at the critical exponent, for example, we see that in general, for the interacting and for the Proca star, which are the ones on the left, I'm sorry that I cannot use the mouse. But yeah, if you look at the interacting in the Proca star fixed points, the critical exponents are relatively stable for the interacting fixed point, of course. For the Proca star, they are stable the more to the Proca limit we approach, and they remain relatively small. But again, for the Gemini, both Gemini 1 and 2, they are significantly big, particularly for Gemini 2. And that is also why we were saying that maybe they do not look very promising. But yeah, in general, we have not only the I'm gonna go back to this one slide here. We have not only the let's say continuation of the Hoyt fixed points, let's say the one with absolutely zero Proca coupling. We have the gauge-like coupling, and we have the genuine Proca coupling. So we were looking for the two regimes, and we kind of found something with the two regimes. No? So in that sense, we are quite happy. How to extend this? So this brings me to the last slide. I'm going to start for the what's next part, if I'm allowed. So the first thing we definitely should do is enlarging the truncation, because we wanted to stick to the absolute simplest case that I introduced earlier, in which, for example, there is this the coupling to the Ricci scalar is entirely the Einstein-Hilbert one, but technically in the generalized Proca construction, one would expect to have this more general function of x that will generate, let's say, this a squared r term that is technically marginal, so that should be included, as for example they did in the Alessia and Sara did, and then it would be quite convenient to include as well the curvature square operators, the r squared and the c squared, which we left outside because they are not part of the general Proca construction. But of course, the flow does not understand that and will generate these terms. So it will be interesting to include those terms as well now that we have a preliminary fixed point structure and see how it changes, if there is any major qualitative, well, both quantitative and qualitative changes on the fixed point structure and basically how they evolve. And of course, at some point also integrate these RG trajectories down to the infrared, translate the fixed point constraints into cosmological predictions, and confront them with observations, which is the final goal of this study, as I said. So that's it. To wrap up, I wanted to highlight these three ideas. The first one is that we constructed a fluctuation-based, not yet, the fluctuation-based asymptotic safety setup for this cosmologically motivated subset of gravity Proca effective field theory. We see that we have quite a rich fixed point structure, including these gauge-like branches, these maybe less important Gemini branches, but definitely genuine Proca type candidates. Like this rich fixed point structure was also something that Alessia and Sara found. And among all the fixed point candidates we have this one that is the genuine Proca type fixed point that only exists, well, not only, but predominantly exists in the genuine Proca limit that has four relevant directions, the usual and expected two gravity ones, but also these two Proca ones. And as we know, this provides evidence for non-perturbative renormalisability of the theory within this truncation. So yeah, it would be nice to see how they translate into cosmological predictions, and in general how they change with the inclusion of new terms. And I think I'm done with it, almost on time. So I can only thank you for attending. And I'm open to hearing any questions you might have or something that wasn't clear enough.
All right. Thanks a lot, Carlos, for the nice talk.